We are group 9, and we're going to be talking about our version of the hemostasis valve.
So for the first thing that we did is we came up with a need statement. The single-use hemostasis valve is used by doctors to seal off or minimize blood loss and ensure unidirectional fluid and blood flow for patients. It is implemented when undergoing diagnostic or interventional procedures using devices with combined outer diameters of up to 8 French, such as aneurysm repair, thromboendarterectomy, dialysis access, etc. This device prevents back bleeding when a catheter or guide wire is inserted or extracted. For the 7 user needs that we came up with and we followed upon is firstly, ensure unidirectional blood flow, decrease the risk of thromboembolism, comfortable and not irritating, cost-effective, quick to use, low infection risk, and simple and easy to use.
It's also our responsibility to research some problems with current hemostasis valves. The most likely reason for a hemostasis valve to get recalled is because of the increased risk of thromboembolism. Pretty much the reason why we have them, so that's not a good thing. Some of these leakages are actually caused from faulty pressure seals, as in the Boston Scientific Guardian 2. Some leakages are caused from faulty gates. Some plastics aren't flexible enough to fully prevent the leakage. Some leakages are caused by misassembly of parts during the manufacturing process when there's multiple parts to be put together. And we also found that Gore-Tex is a material that's already used in some vascular grafts. So we know it's biocompatible and we know that it's incredibly flexible.
I'll be going over the overview of our design. The major problem we wanted to address was air leakage in the hemostasis valve. This air leakage can lead to an air embolism, as pictured on the right. An air embolism is when one or more bubbles of air or other gas is in the circulatory system. Air embolisms can lead to a fatal condition such as stroke or heart attack. To combat this problem that led to several hemostasis valve recalls in the past, we developed a different type of seal, specifically a low pressure chamber. We have increased the length of it to increase resistance and therefore decrease fluid flow. We also added multiple gates, 2 specifically, to prevent the chance of air leakage. There are multiple to use in case one gate fails. The first one uses a push and release mechanism, while the second one is a twist seal used for adjusting to the number of instruments inserted into the valve. Another addition is the use of Gore-Tex in our design. Gore-Tex is a material that is used in many other medical applications, and its microporous properties repel water on the outside, yet is still a breathable fabric membrane while being slightly less expensive than regular materials. Lastly, we incorporated a unibody design that would result in less parts for assembly. This could lead to less labor for assembly and less cost overall to manufacture the device.
This is the Pew matrix our team came up with. Our chosen criteria are device failure, safety, infection, cost, complexity, ease of use, and time to deploy the device. The device failure is the highest weighted criteria, while the time to deploy the device is the lowest. The alternatives for the hemostasis valve our group came up with are a new low pressure seal using multiple gates, unibody design, and a hemostasis valve with a Gore-Tex replacement. After we rated each alternative design based on the criteria, the new low pressure seal had the best score, while the Gore-Tex replacement had the lowest score.
My name is Nicholas, and I will go over our SolidWorks design. We decided to go for a cost-efficient device. The material we use are rubber silicone, pattern plastic, clear plastic, EcoFlex, and Gore-Tex. Our hemostasis valve will have 2 different gates or seal and a pressure chamber that will prevent fluids and air to involuntarily escape or enter the body during the incision of devices. The first seal is a push and release gate that will be open during the insertion of devices or equipment. This seal is made from clear plastic to give more vision to the user. To here, the air will be able to exit as equipment are entering the pressure chamber. The pressure chamber lumen made with Gore-Tex allow the smooth insertion of equipment and stabilize equipment when inserting or removing additional ones. By increasing the length of our pressure chamber, we increase the resistance, which also decreases the flow of fluids. The second seal is a twist seal that can be adjusted depending on the number of equipment being inserted to reduce blood loss. This seal is attached to a flexible shaft that will give more freedom of movement to both the operator and the patient.
This is the design failure mode and effective analysis for a hemostasis valve. The DFMEA is used to determine risks involved in a medical design using the severity and probability of an effective failure. Based on our choices for our design, we have identified failure points in current hemostasis valves on the market. As for the medical use of these devices, it's very important. We have design controls in place to reduce risk using our valve. The primary function of the valve is to deliver fluid to the patient and prevent thromboembolism, and therefore infection through an unsterilized valve pose the highest risk. By implementing the unibody design to make the process of sterilization easier and autoclaving after manufacturing in a clean environment, the risk drops to as low as reasonably possible. All of our design controls have lowered the risk of using our valve and have made it a safer, more practical device for consumers.